Hello, in this video I'll be talking about Bronsted-Lowry acids and bases. So there are multiple different definitions of what acids and bases are. Last semester you learned about the Arrhenius definition of acids and bases. This semester you'll learn about two more, and the one we're going to talk about today is Bronsted-Lowry acids and bases. So what is a Bronsted-Lowry acid defined as? Well, we define a Bronsted-Lowry acid as a compound that donates an H plus ion to another compound and becomes what's called a conjugate base. So essentially, the Bronsted-Lowry acid loses an H plus ion. A Bronsted-Lowry base accepts an H plus ion and becomes what's called a conjugate acid. So the Bronsted-Lowry acid loses an H plus ion and the Bronsted-Lowry base gains an H plus ion. So when you look at a Bronsted-Lowry reaction, what ends up happening is one compound loses an H plus and the other compound gains an H plus, and they form what's called a conjugate pair, where the original acid becomes a conjugate base because it loses the H plus ion, and the base becomes a conjugate acid because it gains the H plus ion. Now, last semester you talked a lot about strong acids, the 6 strong acids and the 6 strong bases, and you mostly talked about those in terms of being Arrhenius acids and bases. Now, there is some overlap in definition. The 6 strong acids can technically be classified as Bronsted-Lowry acids because they all have hydrogen in them, so they can lose a hydrogen ion and become a conjugate base. But most of the time, you're going to see weak acids most of the time with Bronsted-Lowry reactions. You're going to see weak acids and weak bases. And you're also going to see what's called an amphoteric compound. And an amphoteric compound is just simply any compound that can act as an acid or a base. It can be one or the other. And which one it acts as is going to depend on the situation it's in. But essentially, amphoteric just means it can be one or the other. It's not strictly speaking an acid or a base. So with this in mind, let's actually look at an example of what a Bronsted-Lowry reaction looks like and see how we can dissect what you're looking for in terms of labeling. So this reaction here is a really good example of a Bronsted-Lowry acid-base reaction. So to see what's going on here, you kind of have to look at, okay, what compound is losing a hydrogen and what compound is gaining a hydrogen. It's really that simple. It doesn't really get much harder than that. That's the reason I really like Bronsted-Lowry acids and bases. They're just very straightforward in how you can find them. So you really just look for, okay, what loses the hydrogen, what picks up a hydrogen. And if we look at this side of the equation, we have HBrO and we have SO3 minus. And on this side of the equation, we have BrO minus and HSO3 minus. So it looks like HBrO is acting as our Bronsted-Lowry acid because it loses a hydrogen. So you can see here, it loses that hydrogen and becomes the conjugate base. So we'll call this our acid, and we'll call this our conjugate base because it lost that hydrogen ion. SO3 minus looks like it picked up that hydrogen and became HSO3 minus. So we will call this our base, and we'll call this our conjugate acid. Like that. And whenever you have these transformations, whether you lose a hydrogen or you gain a hydrogen, they're called conjugate pairs. So the acid and the conjugate base form a conjugate pair, and the base and the conjugate acid form a conjugate pair. And another important thing to point out is the fact that these reactions almost always happen at equilibrium. So they don't necessarily always move in the forward direction. And actually, the direction of your reaction, whether it moves forward or reverse, or favors forward or reverse, is going to depend on what side of the equation your stronger acid is on. So you're always going to have 2 acids and 2 bases in these reactions. You're going to be judging the acid against the conjugate acid, and depending on which of these 2 is stronger, that's going to determine whether your reaction actually moves forward or not. And so we'll actually be looking at that in the next video, where we discuss how you can determine which Bronsted-Lowry acid is stronger in order to determine the direction of your reaction.